Hello, Calculus. These are the video notes on Lesson 25, Approximating Area. We're actually going to begin this lesson with a review of summation and sigma notation because this is going to be essential when we're calculating the area under a curve. So just a brief reminder, sigma notation is used to represent a sum. We could write 1 plus 2 plus 3 plus 4 on and on until 20, or we could write the sum from index 1 to index 20 of I, and they mean the same thing. Examples using sigma notation. So we're going to write in sigma notation and then evaluate the sum of the terms for 3 to the power of I if I can be 1, 2, 3, 4, 5. Now this one's pretty short. You could probably solve this without using summation notation at all. Just do 3 to the first plus 3 squared plus 3 cubed plus 3 to the fourth plus 3 to the fifth. And thanks to calculators, this wouldn't take you very long. But we're trying to learn the skill of rewriting this in a sum, and your calculator generally has a function that can evaluate summation notation as well, even faster than doing it by hand. So we start with our sigma. We begin with index 1 because the problem has asked us to start with 1, but also because most sequences start at 1, counting, and they have to count by whole numbers. At the top, we're going to count the number of terms. So 1 to 5 means literally 1 to 5. Then here in the argument of the sigma notation, you're going to put your function, which is 3 to the I. Let's open up a calculator and try to do this summation in our calculator function. So here's my calculator emulator. I'm going to hit math, and I'm going to scroll towards the bottom where I can see summation sigma parenthesis and hit enter. Oops. From here, I need to indicate the starting index, so we're going to use x equals 1, the ending index, and the function, and hit enter. And so our sum of terms, which should be 363. But we can always compare that by calculating the actual sum expanded. The fourth, and 3 to the fifth. Same solution. So let's take a look at the second example. In the second example, we're not asked to evaluate the sum, just write the in sigma notation. So we're going to do a sigma starting at 1. This one also has 5 terms, 1, 2, 3, 4, 5. And then we need to determine a function based on the pattern that we can see. So with this pattern, when the index is 1, we get 1. When the index is 2, we get 1 over 4. For 3, we get 1 over 9. For 4, we get 1 over 16. And for 5, we get 1 over 25. And so we can tell that the pattern equation is 1 over something. And then hopefully you recognize this relationship, 2 to 4, 3 to 9, 4 to 16, and 5 to 25 as n squared. Except it needs to say I squared because our variable choice was I. And so that's how you're going to write summation notation when the formula isn't provided. For this next portion, we have a few rules that we're going to be utilizing in calculus, and these are just shortcuts to evaluating the sum. So the sum of integers, starting at 1, can be found with the formula n plus 1 over 2. The sum of perfect squares, starting at 1, squared, here, and then the sum of perfect cubes. There's actually an infinite number of these formulas, but these are the 3 primarily that we'll use to solve area under the curve applications. So here we have 2 more examples. Write using sigma notation and then evaluate. So we'd like to find the sum of the terms I minus 3 quantity squared for I from 1 to 200. This is where we don't really want to expand our sum anymore. So here's I equals 1, ending at 200, and I'm actually going to go ahead and expand I minus 3 quantity squared to be I squared minus 6I plus 9. And we're going to break this sum into 3 parts. So the first portion is going to be from I equals 1 to 200 of I squared, which means we can use that formula from above, minus I equals 1 to 200 of 6i plus the sum from I equals 1 to 200 of 9. Well, this last one's going to be the easiest. This is basically saying how much would you get if you took the number 9 and added it 200 times. So that's going to be 1,800. Now over here, we can actually factor out this 6 and just focus on the sum of I. Pretend like I have enough room here to put the 200. Because if each term has a factor of 6 and you add them all together, you're basically just introducing one factor of 6 to the entire sum. So let's pull out the formula for the sum of I. That's n plus 1 over 2. So in this case, n is the sum number. We're going to be doing 200 plus 1 over 2 with our extra factor of 6. And then the last one is I squared, which is also one of our formulas, and that's going to be n plus 1, 2n plus 1 over 6. I may not remember that when I scroll down. So it's n plus 1, 2n plus 1 over 6. And then we're just going to evaluate the sum using our calculator. Now this may not seem easier than using your summation, but what we're trying to do here with this example is just practice these formulas and applying them when necessary. So we've got 200, 201, 401 divided by 6 minus 6 times 200 times 201 divided by 2 plus an extra 1,800. And voila, our answer is 2,567,900. Let's try that again with our next example. Over here, we have the sum of terms I cubed minus I squared for I is equal to 1, 2, 3, 4, 5, 6. So we're just going to do I equals 1 to 6. And I'm going to go ahead and split these up right away. Since I know that this is the strategy, I'm practicing. And then the I squared formula I still have, which is n plus 1, and 2n plus 1 over 6. But I don't have the n cubed formula, which is n squared, n plus 1 squared over 4. So n squared, n plus 1 squared over 4. And I kind of double check that. Yep. So then simplifying this problem, we get 6 squared, 7 squared, 4 minus 6, 7, 13 divided by 6. 350. And that's specifically using our evaluation formulas. All right, one more example. Again, it's an x cubed, so we're going to be using the n squared, n plus 1 squared over 4. And since the integers are 1 to 10, we know that n equals 10. So we're going to get 10 squared, 11 squared divided by 4. Which is basically just 25 times 121. So how much money do you have if you have 121 quarters? Okay, 3,025. Now we're going to get into the calculus side. So this is going to be the end of part 1 of the video notes, where we're just reviewing sigma notation and some of the basic summation formulas. I'll see you back in the next video where we use these sums to approximate area under a curve.